Hi everyone, we are now in the final module of this course on microsensors and nanosensors. The final module of this course, which is actually the 12th module, is on sensors which is applicable for healthcare, and the module's name is Sensors for Healthcare. So, we all know that sensors are at the core of the modern healthcare innovation, which offers the real-time, accurate and both invasive and non-invasive monitoring of physiological parameters. These sensors are important for various perspectives, including the diagnosis, the treatment, monitoring, rehabilitation, which enables both clinical and remote patient care. Okay. So, these sensors are not only important for diagnosis purposes, but it also helps in real time treatment, monitoring and other purposes for healthcare applications. So, that is why the name is sensors for healthcare, not sensors for diagnostic or sensors for monitoring or something like that. It's sensors are actually applicable for holistic healthcare purposes. Okay. So, if I classify the sensors which are applicable in these applications for healthcare, these sensors can be classified based on various perspectives. This include how these sensors work, what parameters these sensors are evaluating or sensing, okay, etc. Okay. So, based on what parameters these are measuring and how they are measuring, these sensors can be classified as a biophysical sensor as well as a biochemical sensor. We have image sensors for various applications. We will see some of the example, okay, and then we have motion tracker as well as the activity sensors, and then environmental sensors are also equally useful for the healthcare applications. All right. So, irrespective of what sensor you are discussing or you are utilizing, there are a certain desired characteristic of sensors for this particular application. So, the intention of this last two module 11 and module 12 is give you a sense that the sensors that we have discussed from module 1 to module 10 can be applicable, or the characteristic of the sensors can be tuned in such a way that they can be applicable for one application. If you change certain properties, it can be useful for other application. If you remember, in the previous module 11, we have talked about temperature sensors, for example. Okay, we have seen a clear distinction between temperature sensor which is required for industrial application and for a smart building, right. So, we have seen that the requirement, although both are temperature sensors, the requirement of these two applications, one is industrial application, one is sensors for healthcare, the two applications are totally different, and the requirement imposed by this temperature sensor for their application is quite different, right. So, one temperature sensor might be very good for industrial application, but that may not be that effective for smart room monitoring or smart building monitoring, right. So, that is what I just want to mention, that although the sensors characteristic we have seen in more detail in module 1 and module 2, but then we have to see carefully that the application of the sensors that we intend to utilize has to be tuned as per the application of those sensors. Okay. So, the desired characteristic of the sensors for healthcare, irrespective of what sensor you are using, like it has to be biocompatible. Okay. Particularly if you are talking about implantation based sensor, the biocompatibility becomes very much important. Okay. Most of the healthcare sensor has to be miniaturized, because mostly they has to be integrated with point of care devices. Therefore, miniaturization is very important, and that is the reason this MEMS and NAMES based devices has seen real growth in current days. Okay. The sensors that are applicable for this healthcare application has to work on low power, and they have to consume very less power. They should not be a power hungry devices. Okay. So, low low power consumption is another characteristic of the sensors which is useful for healthcare application. Okay, most of the sensor has to be equipped with certain wireless communication antennas or some other ways. You have to integrate it with the wireless communication. Mostly the wearable sensors have NFC enabled, so the sensors are based on mostly this near field communications, but then there are other ways also, like BLE and other protocols which are applicable for the wireless communication of these smart sensors for healthcare. Okay. Then accuracy and calibration mechanism of these sensors are very, very important. Okay. So you cannot rely on those sensors which has to be calibrated every time, and you have to take it to say certain factory or some calibration laboratory to calibrate it every time. Okay. So all these sensors mostly are based on self calibration, or the calibration is as simple as possible. Okay. And the desired characteristic of these sensors are the long term stability and wear resistance. Okay. So you want these sensors, particularly the implantable and invasive kind of sensor, you want a long term stability, because you cannot change it every time the sensor malfunction. Okay. So there are number of sensors which can be utilized for healthcare application. Say for example, a simple speech based sensor, like I am talking. Okay. So if I am having certain say problem while speaking, okay, there are sensors available which can exactly find out that what is the issue in while I am delivering certain speech. Okay. Similarly, we have respiration monitors or breath analyzers. Okay. For number of proteins, number of enzymes, you have n number of sensors available. Okay. So however, it is not possible to talk about all those sensors. So what I have done is I have divided these sensors into 4 different type. One is the glucose sensor, the ECG sensors, pulse oximeters and MRI, which is more important from the electrical engineers point of view. Although all this biomedical engineers and everything is nowadays integrated with electrical engineering, but these sensors are very much essential, and if you understand these 4 category of sensors for healthcare, I think most of the sensors we will understand. For example, if I understand electrochemical sensor for glucose detection, okay, the electrochemical sensor which are utilized to detect certain kind of protein or certain kind of say antibody, okay, they are again based on electrochemical sensor. So if I understand the electrochemical sensor for glucose detection or some other molecule detection, I may utilize that idea of electrochemical detection for the detection of other biomolecules. Okay. So let us talk first about the glucose sensor, and then we will try to cover some of the sensors that we have just talked about. Okay. The glucose sensors based on how you are taking the sample can be divided into 3 categories. You have invasive glucose sensor, you have non-invasive glucose sensors, and then you have minimally invasive glucose sensors also, which are basically utilized in continuous glucose monitoring. Okay. So if I talk about invasive glucose monitors, they are basically they collect basically blood or some other sample in which we have to check the glucose concentration. Usually it is done in blood. Okay. And then we have non-invasive glucose monitors where you do not have to actually take the blood. Okay. And it can be done in the body itself without punching any needle into the body. Okay. So you have optical sensor, for example, the near infrared based sensor which can monitor the glucose in our blood by the infrared light, which can penetrate our skin tissues. Okay. But this is just one way. Okay. There can be other ways of non-invasive monitoring of glucose. Say for example, our sweat contain good amount of glucose. Okay. So if we can monitor this glucose concentration in sweat or any other biofluid which do not have to be taken by punching the needle inside the body, say for example saliva. Okay. Then we have a microfluidic based sensor for monitoring glucose in urine and other biofluids. Okay. And then you have minimally invasive glucose sensor which is based on interstitial fluid. So, exactly you do not need blood, but you have to just pinch your skin and go to the interstitial fluid. Okay. So, these interstitial fluid can be helpful in continuous glucose monitoring as well. Okay. So, out of these, actually the invasive glucose sensors are very popular and is the conventional way of monitoring the glucose. Okay. And usually these invasive glucose sensors are of 5 different type, and these 5 different type of invasive glucose sensors are electrochemical glucose sensor, you have optical sensors, you have thermal devices, the piezoelectric devices, and microneedle based devices. Okay. Optical, although it is a non-invasive glucose monitor, but right now we are discussing under the invasive glucose sensor, because you can have other phenomena, like you can have a sample of blood, and then also you can monitor it through the spectroscopy techniques. Okay. So, right now we are discussing this under the invasive glucose sensors only. Okay. So, let us first talk about electrochemical glucose sensors, okay, which is the backbone of the glucose monitoring devices, and kind of very standard devices for gold standard kind of devices for other emerging device categories. Okay. So, the electrochemical glucose sensors, as I have mentioned, are the key devices which is used to monitor glucose concentration. Mostly this is done for diabetes management, but then there are other applications also where you the blood glucose fluctuate with the time. Okay. So, these electrochemical sensors operate by transducing biochemical information which is present in the glucose or the presence of glucose into measurable electrical signals, mostly in the form of current or voltages through electrochemical reaction. Okay. We will see different architecture of electrochemical sensor, and then we will understand that the output is in the form of current or in the form of voltages. Okay. So, electrochemical sensor for glucose monitoring basically uses a 3 electrode system integrated onto a substrate. Okay. You might have seen glucometers strips, right? They are basically printed with the electrochemical electrodes. Okay. The 3 electrodes which are utilized in the electrochemical glucose monitors are the working electrode WE, the reference electrode RE, and the counter electrodes. You can see a quick diagram of a working electrode and reference electrode working in conjugation with the counter electrode. Okay. So, this is a typically it mimic a electrochemical cell. Okay. So, this is a screen printed glucose monitoring kind of strip. Okay. So, this is your counter and reference electrode, and in between you have this working electrode. We will see what are the functions of this electrode, because this is very much essential to understand the electrochemical sensors. Okay. So, before we actually jump into the discussion on the electrodes, let us quickly see that how this electrochemical glucose sensor works, because if we understand this, it will be also helpful in understanding different generations of glucose sensor and how this glucose sensors has evolved. Okay. So, the glucose interact with the biorecognition element. This biorecognition element can be anything, like it can be a simple enzyme, it can be antibodies, or if it is free of this enzyme and antibodies, it can be simply a catalyst. Okay. So, mostly enzymatic glucose sensors are very popular, and the enzyme which is very popular in this electrochemical glucose sensors are the glucose oxidase. Okay. We will represent this glucose oxidase by this GO. Okay. let us see how this electrochemical glucose sensor actually works. Okay, it will help us in understanding the different generations of glucose sensors and how these glucose sensors has evolved. Okay. So, the glucose actually interact with the biorecognition element. This biorecognition element can be enzymes or antibodies, and if both are absent, like if enzyme and antibodies both are absent, we have catalytic materials or catalytic nanoparticle or simply catalyst placed on the working electrode with which the glucose molecules interact. Okay. Mostly these sensors are enzymatic, so we usually utilize enzymes. Okay. The enzyme which is very popular in monitoring the glucose is the glucose oxidase, and we mostly denote it with this GOX. Okay. And it actually catalyzes. Okay. So, it actually do not participate in the reaction of glucose or oxidation of glucose, but it actually catalyzes the whole equation. Okay. Or whole reaction. Okay. So, this helps in catalyzing this glucose by oxygen to gluconic acid, and as a byproduct you have hydrogen peroxide H2O2. Okay. The hydrogen peroxide which is produced is oxidized again at the working electrode. This oxidation produces oxygen molecules along with the 2 electrons. Okay. These electrons flow through the electrode circuit, and since this circuit is complete, it generates a electric current. Okay. This is a basic working of electrochemical glucose sensors, and based on this fundamental facts, different other generation of glucose sensors has evolved. We will discuss that in a while. Okay. So, now since the idea of electrochemical sensor is clear to us, let us see the electrodes which are utilized in the electrochemical glucose sensor. We already know their names. So, let us talk about working electrode first. Working electrode, as the name suggests, is very important for the electrochemical sensor, and it is basically the heart of electrochemical devices. Okay. Here the glucose oxidation reaction occurs and the signal is generated. Okay. At the enzyme layer, the glucose oxidase enzyme is actually immobilized on the working electrode, and it helps in catalyzing the oxidation of the glucose. Okay. And the material which is utilized in fabrication of this working electrode is mostly carbon, but you will find a lot of noble metals are also utilized, like platinum, gold, okay, which are sometimes modified also with certain nanoparticles, particularly for immobilizing of these enzymes, or for some other applications. We will see that in a while. Okay. So, you have another electrode which is the reference electrode. This reference electrode actually provides a stable and known reference potential against which the potential of the working electrode is measured. Okay. So, it ensures the applied potential at the working electrode remains constant and it should be well defined. Okay. So, despite the sample composition is changing, despite the current is flowing, the working electrode potential remain constant. Okay. So, basically if you see, it is acting as a voltage ruler. Okay. So, it is enabling a precise control over electrochemical reaction by controlling the voltage at the working electrode. Mostly this kind of constant potential can be provided by silver chloride electrodes, and that is why this AgCl electrodes is widely used because of their well known potential as well as very stable potential. Okay. Then you have the third kind of electrode as counter electrodes. Okay. So, this counter electrodes completes actually the electrical circuit by balancing the current which is generated at the working electrode. Okay. Please note that it do not participate in the reaction being measured by, but what it do is it provides a path for current to flow. So, the electrochemical process at the working electrode can be completed without any kind of interruption. Okay. So, for a good counter electrode, it must have a high surface area. Okay, the surface area at least should be large enough to handle the electron flow without becoming a limiting factor in the measurements. Okay, mostly these are made up of inert conducting material. For example, again the platinum, carbon, and gold kind of materials. Okay, so if I summarize this story of electrochemical sensor, you have different electrodes. You have working electrode which conduct glucose oxidation reaction and generates signal. You have reference electrode which provide stable voltage reference. You have counter electrodes which complete the current flowing by completing the path of the circuit. Okay. Then you have enzymes as an important material which is immobilized at the working electrode and it catalyzes specific glucose reaction. Okay. Then you have mediators sometime, okay, which shuttles electron between enzymes as well as the electrodes. Okay. So, depending on what generation of electrochemical device you are talking about, these things are jumbled. Okay. So, if you see the first generation glucose sensor, you have the conventional way of oxidation of glucose by the enzyme production of H2O2 and then electron donation at the electrode. Okay. Similarly, for the second generation, you have now a mediator. Okay. In the third generation, you have this enzymes at place and the electron is directly given to the electrode without having any mediator. And then in the fourth generation devices, it is totally enzyme free and the glucose is directly getting oxidized by certain modifiers, certain catalyst into gluconic acid, and electron is being donated to the electron. Okay. So, if I see the important features of different generation of this electrochemical sensor, in the first generation devices, the principle remains oxygen as a electron acceptor and H2O2 is measured at the electrode and is oxidized, which gives electron. The device is very simple and since it is oxidized by the oxygen, it is much affected by the concentration of the oxygen. Okay. The second generation devices have artificial mediators for the electron transfer that we have just seen. Okay. These devices are less sensitive to oxygen, but then again you have another foreign material present in the form of mediator. Okay. The third generation of devices have direct electron transfer between the enzyme and the electrode, and that is why they have high sensitivity and good response, but then immobilization of these enzymes at the surface of the working electrode is challenging. Okay, and lot of complexity is involved with the immobilization of enzymes. Okay. Then the fourth generation of the glucose sensors are the direct oxidation of glucose at the electrode surface without any help from the enzyme. Okay. So, since there is no enzyme involved, these devices are durable and their lifetime is also better as compared to the enzymatic devices. Okay. However, each of these generation devices has their own limitations similar to the features that possess and that we have just discussed. Okay. The first generation have of course the interferences from oxygen fluctuation. The second generation have potential toxicity, and the third generation devices have limited efficiency and need advanced materials which is coated on the working electrode for immobilization of the enzymes, and fourth generation devices are mostly suffering from the choice of the catalyst for the non-enzymatic oxidation of glucose. Okay. All these generation devices can be based on different architectures. So, you have three different electrochemical sensor architecture. The first is amperometric, which is the basic building block of a glucose sensor. So, most of the devices, glucose sensors that you see around us are amperometric devices. Okay. This measures current as a function of applied voltage. Okay. You have potentiometric devices which measures change in the electrical potential, and then finally you have conductometric devices which measures the changes in the conductivity. Okay. Number of advantages are associated with the electrochemical sensors that we have just discussed. Okay. They have high sensitivity and response is also very rapid. Okay. They are cost effective and suitable for large scale deployment. Okay. The potential for miniaturization and integration into portable and wearable format is still available with the electrochemical sensor, and miniaturized electrochemical glucose sensors are all available in the market. Okay. Continuous monitoring capability is available. So, you can understand that the minimal invasive devices as well as non-invasive devices can also be made up of electrochemical based on electrochemical phenomena. Okay. So, however, there are certain limitations also, like if you talk about enzyme based sensors, they are limited by the enzyme stability, which is of course affected by the pH, temperature and other ambient factors. Okay. They have short lifetime and they have manufacturing complexity. For non-enzymatic electrochemical sensor, they are prone to the interference and surface fouling. Selectivity over the physiological compounds has to be ensured, because we do not know in the non-enzymatic based devices that what is getting oxidized, it is glucose or glucose essentially, or it is some other molecule or other carbon molecule which is which you are measuring. Okay. So, this is the fundamental of electrochemical sensor. The same kind of devices can be used for non-invasive as well as for minimally invasive devices. Okay. However, of course, the molecule that you are detecting remains same. However, the fluid that you are dealing will be different. Like here we are talking about glucose present in blood. There can be the interstitial fluid, or it can be sweat or saliva, whatever, depending on what device you are, what fluid you are using. Okay. Then along with the electrochemical sensor, we have another kind of devices which is known as optical devices, and optical glucose sensors are also very popular, and nowadays it is emerging as a non-invasive kind of device. Okay. So, optical glucose sensors detect glucose by measuring change in the optical properties when glucose interact with the light. Okay. And when light and matter interact, there can be a number of phenomena that can occur, and based on these phenomena, utilizing this phenomena, people has come up with number of optical glucose sensors. Okay. So, let us see quickly that what kind of devices are possible with the optical phenomena in place. Okay. So, say the key mechanism is, for example, the absorption. Okay. So, you have two different kind of spectroscopy based glucose sensor. They are the near infrared spectroscopy, the NIR spectroscopy, as well as the MIR spectroscopy, which is the mid infrared spectroscopy. Okay. Based on scattering of light by glucose, you have optical coherence tomography, OCT. Then based on the rotation of the molecules, you have the polarimetric glucose sensors. Okay. Based on the emission, you have fluorescence and Raman based devices, and based on diffraction, you have holographic sensors. Okay. So, let us quickly see about the near infrared spectroscopy based glucose sensor. Okay. The NIR spectroscopy uses light in the wavelength of 1.6 to 1.8 micron. Please note that when I am saying 1.6 micron to 1.8 micron, I am strictly talking about the glucose sensor. Otherwise, the NIR spectroscopy can utilize anything, any wavelength from say 700 to even 2.5 micron and sometime even beyond that. Okay. So, for example, we have discussed about NDIR gas sensors, okay, near non-dispersive infrared sensors, where we have utilized the infrared radiation for the detection. Okay. We have seen that of course, you can utilize the mid infrared as well as far infrared also, but it was mostly concentrated in the near infrared region. So, near infrared spectroscopy, if you strictly talk, it is anything from 0.7 to 2.5 micron However, for the glucose monitoring, it is utilized in the range of 1.6 to 1.8 micron. Okay. So, this devices relies on the absorption of the NIR light by number of vibrational modes of glucose molecule. There are number of bonds available in glucose like CH bond, OH bond and CO bond, right. So, depending on their vibrational modes, you can have absorption of NIR lights, okay, near infrared lights. Okay. The mechanism of NIR spectroscopy based optical glucose sensor is pretty simple. You have a light source which emits the NIR light towards the skin. Okay. It can be mostly on the fingertip or at the forearm, okay, depending on what kind of tissue you are targeting. Okay. Then this NIR light interact with the tissues. So, light penetrate the tissue and interact with the blood as well as the interstitial fluids. Okay. Then you have the absorption spectrum where glucose absorbs light at a characteristic wavelength of about 1.6 to 1.8 micron, okay, and then you have detector which capture the transmitted or the reflected light. Okay. So, this is how a basic NIR spectroscopy based glucose sensors monitor. It has a source, this source interact with the tissue, there is absorption of the spectrum and then you detect the transmitted or reflected light. Okay. There are n number of advantages of NIR spectroscopy based optical glucose sensor. The first and foremost advantage is it can be a non-invasive. So, basically no blood sample is required. You are measuring direct blood inside your body basically. So, you are not actually extracting any blood drops. Okay. So, they are basically can be non-invasive. Okay. Real time monitoring is possible. So, it enables continuous glucose tracking kind of devices. Okay. And they can be miniaturized and portable device can be fabricated using by fabricating this NIR spectrometers on the MEMS platform. Okay. However, all are not always good. You have various limitations also of the NIR spectroscopy, like the biggest disadvantage of this kind of device are their low selectivity. So, water and other tissue components can also absorb NIR light, and anything which absorb light in the near infrared is a threat for the selectivity of the NIR spectroscopy based optical glucose sensors. Okay. Then you have signal interferences due to skin tone, hydration and variation in the temperature. Okay. Then calibration of these devices require complex multivariate calibration models. Okay. And the penetration depth is also associated with the kind of tissue and tissue penetrations. Okay. Some of the answers of these limitations can be given by the mid infrared light, where you have a little larger wavelength of infrared that are in picture. Okay. So, we will talk about the mid infrared spectroscopy in the next class, as well as we will discuss other kind of glucose sensors in little detail in the next class. Thank you.